In this video, we're going to talk about how we can transition now from knowing the average rate of change to learning the instantaneous rate of change now that we know how to find a derivative. So far we've seen how derivatives can be used to determine the slope, or the slope of a tangent line, or the slope at one point, right? Well, we're going to use that idea here in a second to find the instantaneous slope or rate of change of a certain function. We use rate of change in lots of different applications. We can use it for like production rates, population growth rates. We even use it a lot in physics to talk about velocity and acceleration, right? Velocity is the change in position over time, or rate of change of your position, right? And acceleration is your change in velocity over time, so another rate of change. And in our pre-calculus classes and in our algebra classes, we were stuck just looking at average velocity or average rate of change, right? If we're talking about a position, we can find the rate at which it's changing, the velocity over a time period, or an average velocity. Or we can find the change in our distance over our change in our time, right? Our average rate of change over our average velocity, right? Which is just a fancy way of saying the slope between 2 points. So we can look at example number 9 and see that with our pre-calculus knowledge, we're stuck just finding the average velocity, or the velocity over a little time interval. And in a second, in the next video, we're going to talk about how we can find the instantaneous velocity, how fast something's position is changing at one exact moment. So in example number 9, it says if we have a billiard ball and it's dropped from a height of 100 feet, its height s at time t is given by the position function s equals negative 16 t squared plus 100, where s is measured in feet and t is measured in seconds. So this is the position in feet at any second. I can figure out where this ball is at any second in time. But the question doesn't ask me for where is it at, the position. It's asking me to find how fast its position is changing, the velocity. If we were talking about just the average velocity, we would be really talking about over 2 time periods, or an interval, right? The slope between 2 points, the velocity over a time interval. So we can see that the first time interval is between 1 and 2 seconds. The next one gets a little bit closer, between 1 and 1.5 seconds. And then the next one gets us even closer, 1 to 1.1 seconds. We can find the average velocity over these 3 time intervals by simply using our slope formula, our change in our position over our change in time. So we have our change in our position. We can plug in our s of 2 minus our s of 1 over 2 minus 1, right? That's our y2 minus y1 over x2 minus x1. Now remember, our s is our position, and remember our position is in feet. So here's where units are kind of important. I don't just want you to be a robot and plug in numbers and not know what those numbers mean. Because we are now talking about an application problem, we need to know what our answers mean and not just have an answer that doesn't mean anything. So when we're substituting in and we're plugging in 2 for our t, and our 1 for our t, what we're really finding is our ball's position, right, in feet. When we take our 2 minus 1 in the denominator, what we're really doing is finding our change in time in seconds. So you can see that I've kind of put my units there to help me figure out what our answer represents. When I end up calculating it, I get a negative 48. But really, it's a negative 48 feet per second. What this is representing is the average velocity, the speed at which this ball is falling between 1 second and 2 seconds. It is falling at a rate of 48 feet per second on average over that 1 second time interval. You might notice that it's a negative velocity, which helps us figure out what direction it's moving, right? It's obviously dropped, so it should be falling down. But there's going to be other problems where you don't necessarily know how it's moving, and so your answer will help you figure out how it's moving at that time. If it's negative, it's moving in the negative direction, either down or left typically. If it's positive, it'll be moving in the positive direction, up or right typically, okay? Now, what if we wanted to figure out what was happening at exactly 1 second? Again, with our pre-calculus knowledge, if we didn't know how to find the slope at one point, right, a derivative, we would have to just estimate it by moving those 2 points closer and closer together. Let me show you a visual representation using a Desmos graph of what maybe this would look like, right? So we have our function in here of our billiard ball falling, and we have 2 points on our graph, and it started from 1 to 2, right, our 2 points. And then what we're going to do is we're going to move those 2 points closer and closer together so we can eventually figure out what's happening, how fast is this ball moving, instantaneous velocity at exactly 1 second, at that 1 point, right? And that's where we need to use our ideas of derivatives to help us figure that out. All right. So we can get our points closer and closer together. We can move it between 1 and 1.5 seconds. We can evaluate our average velocity, and we can say that between 1 and 1.5 seconds, this ball is falling at a rate of 40 feet per second. You can see that the numbers are going down slightly. What if I move it closer, between 1 and 1.1 seconds? You can see that the ball is now falling at a rate of 33.6 feet per second. Between 1 and 1.1 seconds, it's falling on average at about 33.6 feet per second. So, what if we wanted to figure out how fast the ball was falling at exactly 1 second? This is where we're going to use the idea of derivatives and instantaneous velocity to help us figure out what's happening at exactly one moment in time, not over a time interval anymore. So not an average velocity or rate of change, but an instantaneous velocity or rate of change. We'll talk about that in the next video.